Hello again, and welcome to YCP Chemistry Labs, your college's YouTube channel for getting you ready for General Chemistry Lab each and every week. Today we'll be discussing our Density Calculations Part 1 experiment. And it shouldn't take long to get ready for this relatively simple experiment. So let me get right into highlighting the details of today's work and get you on your way. This is a two-part lab. And in today's work, we'll be collecting data that we'll be using next week to determine the density of rubber. So we're going to use some rubber stoppers, which are oddly shaped, awkwardly shaped, which is part of the challenge of determining their density. Last week in lab, you played around with some objects that were different sizes and shapes, but they were all items that were cubic or rectangular or even a cylinder. Very easy to measure their dimensions, and that allowed you to calculate their volumes from those dimensions. And then you determined the masses from the electronic balance. These rubber stoppers, as you'll see once you get your set in the lab, are not quite perfectly cylinder shaped. They're tapered. This is by intent for allowing them to fit into glass objects. And that makes it hard to determine their volume in the same way that we did last week in lab, which presents the challenge or slight challenge for us to overcome in lab today. So that's the main purpose or goal of our work today. But like last week, we'll get another chance to practice using the correct measuring techniques on the different measuring tools that we have available to us. So today we'll be using the electronic balance, which has no uncertainty as far as we're concerned, or we don't have to worry about the rules of uncertainty when we weigh an object on the electronic balance. But we'll be using the graduated cylinder to measure volumes, again, like we did in the fundamentals experiment as well. And our graduated cylinders for today's work are marked off in whole milliliters, so that'll be important for a little bit later on. And then in our second approach, we're going to use an object that seemingly has less accuracy associated with its markings than the graduated cylinder does, but I'll walk you through how this object hopefully will become a more accurate way to study the density of our rubber stoppers. But all the while, we want to focus on what are the correct number of significant figures and carefully performing our measurements so that we have a nice, accurate, reproducible answer. And then our third goal, which really won't come into play until next week when we do our data analysis, will be to compare the two different approaches that we use in lab today. There are often many different ways to solve a chemical problem, and one of the first choices a chemist has to make is what approach will they use. Some methods are fast, but maybe less reliable. Others involve significantly more work, and thus might be a little more reliable. So we're going to sort of demonstrate that idea through the choices of method that we have waiting for us today. So the two methods that we have are displaced volume and displaced mass. In the displaced volume method, we take a rubber stopper and we drop it into an object containing a liquid with known volume. And the object then displaces some of the liquid in the graduated cylinder or a beaker. And you simply measure the difference in order to determine the volume of the object. Now, the choice of object or the choice of measuring tool is important in terms of the accuracy of your answer. If I tried this in a beaker with very few markings on it and dropped the rubber stopper in, so let that be my rubber stopper, the volume might go up some small amount, but that would be very challenging to read the difference. What is the change in volume in this case? There isn't much of a scale here to help me discern how much the water level in this case has risen. If we're using a graduated cylinder, though, with much more markings on it, and we drop our rubber stopper in, we would have a change in volume that is now much more easily read. And remember, because this graduated cylinder is marked to the milliliter, we can read the volume to the tenths of the milliliter. All right? So we could be looking at more significant figures in the volume measurement that we have here. Either one of these approaches, unfortunately though, would limit the number of significant figures that we're going to get for the mass of these objects. When we weigh our rubber stoppers on the electronic balance, we're going to get anywhere from probably between 1 and 10 grams per rubber stopper, but that's going to have 3 or 4 decimal places at least after it, depending on the precision of our electronic balances, typically set to 3. So this is going to have 4 significant figures compared to our volume over here, which would have 2 in the case of the graduated cylinder, and perhaps only 1 read off of a beaker. So when we calculate the density of this object by taking its mass divided by its volume, if we have something with 4 sig figs divided by a value with only 2 sig figs, our resulting answer can have at most 2 significant figures according to the rules of performing calculations and accounting for significant figures. That's a pretty big hit to take, especially if we've gone through a lot of trouble to get a very accurate measuring of the mass of the rubber stopper. So the displaced mass method will allow us to calculate the density using only mass measurements. And thus all of our masses would be measured to the same number of significant figures, and in the end we would have a volume that would have 4 sig figs as well. Thus our density should also have 4 significant figures. So how are we going to accomplish this displaced mass method? In the displaced mass technique, we'll use a small Erlenmeyer flask with a lid on it. You'll fill the flask first entirely with water, completely to the top, so that when you put the stopper in on the top, water actually splashes out over the sides. This is very important. We don't want any air bubbles inside this. We are trying to figure out its true volume. I know there are markings on the side of this, but they stop at 50, and clearly there's some space above that. We're trying to figure out the true volume of this flask. We're going to fill that flask completely with water. If we have weighed that flask before and after filling it with water, the mass of water in the flask can be used to determine the volume of water, which is the volume of the flask. How is this accomplished? With the density. Using the density formula, we could simply manipulate it. Volume would be mass divided by the density of water. So that becomes a very carefully defined volume then. If we now remove the stopper and place one of our rubber stoppers inside it, or 2 or 3 for that matter, they are, just as in the case of the graduated cylinder, they are going to displace some of the water inside this Erlenmeyer flask. In some cases enough that more will spill out over the top. And certainly when we put the ground glass stopper back in the top, we'll spill water out again. But now we're going to have a different mass of this combination in total, because the rubber stoppers have a different density than the water that they are replacing. So if we re-weigh this entire combination now, there's going to be a different mass, more or less depending on the density of the rubber. Okay? Now, it shouldn't take you long to realize the rubber stoppers, you'll see them sink to the bottom of the flask, meaning they are more dense than the water. So their mass is greater than the volume that they are displacing. Right? And this, I just want you to remember this as you go through your calculations. Sometimes you'll trick yourself into thinking that you're looking at this backwards if more volume hasn't been displaced. But the rubber is more dense, and that's why it sinks to the bottom. We want to imagine, and this is described in next week's work, it won't be important for today, this is a seesaw system. The total amount that we had before we added the rubber stoppers and after is equal if we look at the water and the rubber stoppers as separate systems before, and then the rubber stoppers inside the flask after, and the displaced volume after. That's what we're really trying to calculate, is the missing amount of water. And that's what we'll be looking at in next week's work. For today, the work is quite simple. You'll have your 3 rubber stoppers, which will give you 6 combinations for determining the density. This will give us hopefully a reproducible result, something we like to have in scientific work. Rather than just one data point, we like to gather as many as possible. So each stopper by itself is a data point that we can observe, and then each pair, the biggest and the smallest, the middle and the biggest, the middle and the smallest, and then all 3 all together, gives us 6 different combinations to study. Now they're all the same rubber, so the density should always be the same. Although the specific mass and volumes will be different in each of those 6 cases that you look at. All right? So as I was just saying before the camera shut off, the tools are pretty simple and straightforward. We'll need a graduated cylinder. We won't be performing any volume measurements with a beaker, as I had described earlier. Just way too much uncertainty associated with that. So we'll use the graduated cylinder, and then we're going to use the Erlenmeyer flask. Now once we've carefully defined its volume, we call this a pycnometer. That's an apparatus, any apparatus or measuring device whose volume is precisely defined based on the density of the liquid that it contains. So that's what our Erlenmeyer flask will become for us, a pycnometer. So there are 2 parts to the work, using the graduated cylinder for displaced volume and the pycnometer for the displaced mass. At the end of lab today, your lab notebook, you have a page for collecting your data in there. And I would suggest that you use one side or 1/2 of this for your displaced volume method and 1/2 for your displaced mass method. And you'll want to bring this data to lab with you next week, since we'll learn how to use an Excel spreadsheet to analyze the data. While it's only 6 data points for each method, which might not sound like a lot, we can learn or train ourselves how to use a spreadsheet to perform these calculations that are redundant, that we're doing the same thing again and again, and it becomes a real time-saving mechanism for us. Imagine if we were trying to measure the density by looking at 50 different rubber stoppers. You wouldn't want to calculate all of those by hand on a calculator. So we're going to train ourselves how we can use a spreadsheet to analyze a large data set in lab next week. As for your pre-lab for today, the 3 questions I think you'll agree are pretty straightforward. We've already talked about the formula for density. Density is simply the ratio of an object's mass to its volume, so mass divided by volume. Given that mass can be recorded in many different unit sets and volume can as well, you can have many different combinations of units for density. Simply pick a mass unit and divide it by a volume unit, an appropriate volume unit. And this will give you the a set of units for density. Be on guard though. Don't confuse mass with weight. The weight of an object is really its force when it's exerted upon by gravity. So pounds, for example, which sometimes we confuse with mass, is not technically a mass of an object. Pounds are the force the object is exerting due to gravity. So you want to pick some mass unit and divide it by some volume unit. Now there's a standard for each of those quantities. For mass, the standard is kilograms, and for volume, the SI unit would be the meter cubed. And those would technically make up the standard units for density. And in your third pre-lab question, you need to perform a simple calculation and take into account the significant figures, just as I had described earlier in the lab. So they should be three pretty quick and easy, straightforward pre-lab questions for you to take care of this week. When you leave the lab today, be sure to show your instructor your data set and to bring that lab manual with your data back to lab next week so that you and your partner can begin the data analysis and compare the two different methods, displaced volume and displaced mass. All right? That's it for now. We'll see you next week in lab, and I'll wish you happy measurements and good luck.